So can everyone see the screen? Hello? Okay, great. So today is the final class where we'll clear all the doubts and go over all the material for the course. So does anyone have any questions or any doubts or anything that they would like to ask right now, or probably some part where you're not clear and you want me to explain it to you again? If there's something like that, please, uh, yeah, we can do that first and then go over everything. Please feel free to unmute yourselves or type anything in the chat box if you have any questions whenever. Same questions as in Sheikh. So the kinds of questions you have in your assignments, you will get similar kind of questions in your final exam, but they won't be the same question. How to use the scientific calculator? Okay, uh, 1 second. Does anyone have the link to the calculator? This is the one, no? Yeah, thanks. So you use it as a regular calculator only. So let's say you want to do some simple things, you can do it like this. C is basically for clear. Then you have these trigonometric functions and some constants like pi, e. You can use this to get factorial. For example, if I type 10 and type this, so it's basically 10 factorial. It gives me the answer of 10 factorial. Okay. Then similarly, if I write 2 and then press this e to the power x, it'll basically take e to the power 2. So basically square of e. Right. So yeah, it's mostly these simple things. So this is for exponential, this is for log 2, this is for log base something else. So basically, let's say 10 base, I type 10. So basically, it's first you type whatever you want the log of, then you press this, then you type the base and you press equal to. So you get the log of that. So log of 10 base 10 is 1. Right. Then this is similarly for the others also. Here you get for a cube, so basically 2 cube. Uh, if you want to raise 2 to the power of 6, then you can do it like this. So 2, then you press this, and then you press 6. Great. Sorry. How to use it for eigenvalue and eigenvector. So when you are given in the exam questions, it will basically be, 1 second, I'll open that week's lecture. So when you are given questions in the exam, it will be mostly from 2x2 matrices, okay, where you can easily find the determinant and the, what do you say, inverse and everything. Eigenvalue and eigenvector you don't need to calculate, right? So things which require heavy computation or things that require mathematics that you have not been taught in the course won't be asked in the course. Whatever you will be asked, you will be able to solve using this scientific calculator. Okay. So most likely you won't be asked to uh, solve for eigenvalues and eigenvectors. So don't worry about that. But you can still ask in the discussion forum about what exactly kind of questions will come and how much competition will they require, right? Because there are more able people there who can answer these questions. Apart from that, you can, whatever functions are here, you can use that to carry out any computation that you want. So basically, let's say if I want to calculate the mm, determinant of some matrix, for example, if I want to calculate the determinant of this, I need to do this multiplied by this minus this multiplied by this. That I can pretty easily do by hand, but if you have fractional values or something that you can't, then you can easily use the calculator to do these calculations, right? Uh, you won't be asked to calculate eigenvalues and eigenvectors because I don't think you were taught how to do that by hand, and you won't be given R. Like you can't use R in the exam hall. So at most, the type of questions that you will get will be similar to this. So you'll be given, let's say, 3, 4 matrices and one eigenvalue, and you'll be asked to find which is a matrix corresponding to this eigenvalue, or you'll be given, let's say, things like this. Uh, let's say you are given lambda is an eigenvalue of m, find the corresponding eigenvector, or you are given this is the eigenvector of m, find the corresponding eigenvalue, or things like that you will be given mostly. So things that require matrix multiplication and all. And that's pretty simple to do using the calculator. No, I don't think you will be given R to use in the exam. I'm not sure. You can ask in the discussion forum and confirm once. But as far as I know, uh, you are not allowed to use R. The only thing you'll be allowed to use is this online calculator. Okay. Does anyone have any more questions? Okay. Uh, someone is typing.
Hello.
Yeah, hi.
Yeah, hi, I'm Akshadaya. So, do we need to write some R script or anything in the exam? So, will there be questions like write a script for this or that?
Uh, I don't think so. As before, you should ask this question in the discussion forum. but you might get questions like this. So you will be given some R code, and you need to analyze that and uh, make inferences based on that. Sorry.
So mostly we'll get objective questions, not subjective, right?
Yes, I think so.
Okay, thank you.
Okay. Does anyone else have any more questions? Okay. So we'll recap whatever was done in the course. Uh, so basically, in week one, we learned about probability. We learned about what are mutually exclusive events and what are independent events. So we also talked about the addition rule and the product rule in probability. So mutually exclusive events are events that do not occur together simultaneously. Okay. Independent event to say that two events X and Y are independent of each other means that if X happened or did not happen, it will not change the outcome of whether Y will happen. So basically, the probability of Y happening does not depend on the probability of X happening and vice versa. Okay. Then in the first week, we also talked about random variables. We talked about probability distribution, such as binomial, multinomial, and Poisson distribution. Uh, we talked about probability mass function and probability density function. Uh, then also at any point, if you feel like you want more explanation or you feel like uh, you have a doubt related to that topic, you can ask. Okay. Uh, yeah. So then we also learned about probability density functions for continuous functions, which is given by this formula. We talked about three commonly used continuous distributions: the uniform distribution, where the probability of everything is constant, is the same; normal distribution, which is also a Gaussian distribution; and also exponential distribution. We also talked about cumulative distribution function, which is basically the cumulative graph of increase in probability. I think there will be calculation questions uh, based on probability distributions. So, okay. Ah, so you had these kinds of questions in your uh, assignments, no? So these kinds of questions will be there. Numericals, where you have to calculate the mean standard deviation, or uh, yeah, for distributions, you have to calculate the means and all standard deviations. And you also need to remember these formulas for different distributions. Uh, yeah, I think that answers the question. So solve it using scientific calculator. So let's you want to do this question. Okay. For the following data, calculate the standard deviation with Bessel's correction. Okay. So so basically, this standard deviation is the root over of this. Uh, else have we written it? Okay, we haven't written it anywhere. Anyways, so basically, what we need to do is we need to like we did here. These questions we would have. Okay. Uh, just add a slide. Okay. So the question is, for the following data, calculate the standard deviation with Bessel's correction. Data is 5231451. Basically, 5, 2, 3, 5231451. 1451. So this is basically our x, right? So standard deviation is given by x minus x bar. This formula, right? So first we need to calculate the mean. So basically x bar is equal to, will be the sum of all of this. 5, 2, 3, 1, 4, 5, 5, 6, 7, 8, 9, 10, 11, 14, 19, 20. It's 20 divided by 1, 2, 3, 4, 5, 6, 7. 7 is basically equal to, so now we'll use the calculator. Now we'll use the calculator. T divided by 7, 2.857. Right. So it's 2.857. Then what we need here is x minus x bar, right? So we just subtract 5 minus 2.857. 0.143.
So
Yeah,
the total would be 21, right? Not
1
20.
second. 5, 6, 7, 8, 9, 10, 11. Ah, okay. It'll be 21. Sorry. Ah, okay. So x bar is basically 21 divided by 7, basically 3. So I minus 3 is basically 2. 2 minus 3 is minus 1. 3 minus 3 is 0, 1 minus 3 is minus 2, 4 minus 3 is 1, 5 minus 3 is 2, 1 minus 3 is minus 2. Then we need x minus x bar square. This is 4, 1, 0, 4, 1, 4, 4. We need the sum of this. 4, 5, 4, 4, 8, 9, 10, 18. Okay. This is 18 divided by n minus 1 is 7 minus 1, 6, root over of this. So it's basically root over of 3. Now you can use the calculator to, where is root over of 3. So you write 3, you do this, then you take 2 here. Okay, so this is basically root over of 3. So first you take 3, then you take this root over sign. So basically you are taking root of 3. And which root do you want? So you want the square root. So 2. So we'll type 2 and we'll press equal to. So it's 1.732. 1.732. You can check. Yeah, that's the answer also. In the exam format, it was written question type MCQ. So you have to type it, no? Your computer will have a keyboard.
Yes, sir.
Yeah, you can type the set questions. Then, yeah. So in the first week, basically after this, is it clear how to use the calculator? Like, I'm not sure what else I need to show. So like, it's basically mostly like a normal calculator. These functions, you need to first, whatever you type will be the x value first, and then you click the function, and if there is a y value, you can set it later. That's all there is to it. And the C basically clears it. So you write 2. So this, and you want to raise 2 to the power 3. So you'll press this. So the value of x will be 2. Then you press 3, that will be the value of y, and you press equal to. So it's basically 2 raised to the power 3. Similarly, for root over, if you want the cube root of 2, you type 2, you press this, and you press 3. It's basically the cube root of 3. So, yeah. Okay. So we also talked about moments in data, mean and variance of the data. How does variance change if how, like, so variance of x and y is given by expectation of x square into expectation of y square minus expectation of x whole square into expectation of y whole square if x and y are independent. And if x and y are independent, the expectation of x into y is equal to the expectation of x multiplied the expectation of y. Okay. We also talked about variance. We talked about Bessel's correction where we have this n minus 1. Okay. So if you take variance of the sample without n minus 1, what you get is a biased estimate because you want to estimate the variance of the population. So we do some correction, which is called Bessel's correction, which basically gives us this denominator of n minus 1. We talked about covariance, which is a measure of joint variability between two random variables. So basically, how do they co-vary? If x increases, what happens to y? If y increases, what happens to x, and so on. And the most important thing to note here is that x and y, if x and y are independent, the covariance of x and y will be 0. However, if covariance of x and y is 0, it does not mean that x and y are independent. Right. Then we talked about conditional probability, Bayes theorem. So basically, probability of x given y is given by probability of x and y divided by probability of y. And Bayes theorem basically says probability of y given x is equal to probability of x given y into probability of y divided by probability of x. Right. Then we talked a little bit about hypothesis testing and also about t-test. So hypothesis testing is basically uh, we are testing if the observations that we have seen in our samples, do they hold true for the population also? So we have a null hypothesis, which is basically a statement of no difference, or like, yeah, basically it's a statement of no difference or equality. So if you have two samples and you're comparing their means, your null hypothesis would be that the means are equal. And your alternate hypothesis would be the means are not equal. Then you calculate some test statistic, like using some statistical test, let's say a t-test or something, you calculate a test statistic, which is a t statistic, and you check how high or low it is compared to a critical value in a t table, and that gives you the probability of it happening. If the probability is less than a certain threshold, which is also called the level of significance or alpha, you then reject your null hypothesis. If it is not less than the significance level, then you say it's basically uh, if the p-value you get is not less than the significance level, then you basically cannot reject your null hypothesis. And let's say you're comparing two means of two distributions. If your p-value is less than your level of significance, let's say 0.05, then you say that statistically there's a difference in means. However, if your p-value is greater than 0.05 or whatever boundary you set, then you say that there is no difference between the means. Right. The most important thing to take away from here is that statistically significant does not mean that if your result is statistically significant, it does not mean that it has any biological or clinical implications. Right. So, something can be significant, but the change might be very low that there is no biological effect or there is no clinical implication of whatever is happening. So that is something that you need to decide based on the experiment you are doing and on the kind of data that you are basically trying to work on. Right. That was it for week one. We'll just go over everything. Uh, In week two, we talked about basic concepts of linear algebra, where we talked about vectors, how to add vectors, how to transpose vectors. So basically, addition is simple. If you're adding two vectors, you basically add them element wise. Transposition is basically rows become columns and columns become rows. Scalar multiplication, if you multiply a scalar with a vector, then each element of the vector is multiplied by the same scalar. Length of the vector is also called the norm. So it's basically you square each of the elements of the vector, add it, and take the root of it. Dot product is basically element-wise multiplication and then addition. And projection is basically when you're trying to project one vector on top of the other, how do you get that? So you get the angle between vectors and the projection of vectors. Right. So if we are projecting the vector uh, V on U, then the projection of V on U is given by dot product of V and U divided by the norm of U into U. So the U vector. Right. And uh, basically the angle between two vectors theta, cos theta is given by U dot V divided by the magnitudes of U and V. Uh, then we talked about matrices. What are the different kinds of matrices? Rectangular, square, zero. So rectangular is basically number of rows and columns are different. Square is basically number of rows and columns are same. Zero matrix is full of zeros. Diagonal matrix only has diagonal entries. Identity matrix only has one on the diagonal and zero everywhere else. We talked about how to add two vectors. So you basically, if you're adding two vectors like this, you basically add their elements. Scalar multiplication is the same. You multiply a vector by a scalar. You multiply every element with a scalar. Matrix multiplication is basically, let's say you're multiplying two matrices. You first take the row of the first matrix and then multiply it with the column of the second one. And you write the value here, add it. So basically 1 into 1 plus 2 into 5 will be here. Similarly, 1 into 3 plus 2 into 6 will be here. 3 into 1 into plus 4 into 5 will be here. 3 into 3 plus 4 into 6 will be here. Okay. Uh, then, then we talked about the determinant, which basically represents the area of the parallelogram formed by two vectors. Right. So the determinant of two vectors is 0. They lie on the same line or span. We talked about how to calculate the determinant for a 2 plus 2 matrix. So for 2 plus 2 matrix, it's basically the main diagonal, multiply the element and subtract from it the elements in the other diagonal. So 2 into 4 minus 3 into 1. Or in this case, 1 into 6 minus 2 into 3. Right. So if the determinant of a matrix is non-zero, then that means the matrix is a full rank matrix, or the rows and columns are independent of each other, linearly independent. However, if determinant of a matrix is zero, then there are some rows or columns which are not independent of each other. For example, in this case, we calculate the determinant to be zero, and we can see that the second row is basically twice of the first row. Right. We also talked about inverse. So inverse is basically, so if you have a matrix A, then A inverse will basically have the property A multiplied by A inverse. If you do matrix multiplication, you get the identity matrix. Okay. Only a full rank matrix can have an inverse. So only a matrix which has a non-zero determinant will have an inverse. Not all matrices have inverse. Yeah. And yeah. Basically, we are all only in this case talking about square matrices, not rectangular matrices. Uh, then we talked about eigenvectors and eigenvalues. So eigenvectors and eigenvalues for a given matrix are basically vectors and vectors. Eigenvectors are vectors which follow this equation, which when multiplied by the uh, matrix, give the same vector scaled by some unit. So the scaling factor lambda is called the eigenvalue, and the vector v that remains unchanged is called the eigenvector. Okay. And yeah. Then we talked about a system of linear equations, right? And how to solve them. So let's say we have a system of linear equation. We can express it in the form of ax equal to b, right? So basically, yeah. So basically, in this case, it's ax equal to b. So b is the constant vector, x is the variable vector, and a is the coefficient matrix, which we get from our equations. Okay. So our A matrix, coefficient matrix, will be a M cross N matrix, where M is the number of equations and N is the number of variables. Right. When M equal to N and the determinant is non-zero, we have a full rank matrix. Then we have a unique solution. So we can find X by X equal to A inverse into B. However, if the system is overdetermined or if M is greater than N, or if like the number of equations is more, then the system has no solution. If the system is underdetermined or M is less than N, So it has less number of equations than the number of variables. The system is underdetermined and it has infinite solutions. Okay. Uh, then we also talked about eigenvalue decomposition and singular value decomposition, where we basically break any rectangular matrix into uh, basically diagonal matrices because these are easy for us to compute on. Right. So that's it for week 2. Then in week 3, we talked about basics of R. So basically, I think now everyone has installed R and is comfortable using R. However, we'll just go over the basics one more time. So this is basically your uh, source window where you have your script. This is your console where you execute code. This is your file pane where you have file. You can also view your plots and everything else. This is the environment pane which contains all the environment variables. You can go to session, set working directory, choose directory to set a working directory. You can go to tools, install packages, and type the name of the package to install it. Right. So, and we talked about basic multiplication and other things that we talked about variables and other things that you can use, functions and all that you can use in R easily. Mm, Then on week 4, we talked about data visualization. We talked about different kinds of plots, such as scatter plot, which is typically used to visualize two numeric variables. We talked about bar plots, which basically helps us plot numeric variables for different levels of a categorical variable. We talked about histograms, which shows the distribution of a given variable. And we talked about how we can create a histogram from raw data. Basically, we have some raw data, we bin the data, and then in each of the bins, we basically calculate what is the number of uh, occurrences of the given data. So in this case, we are counting marks. How many times is the mark between 0 and 10? Only once. So here it's 1. How many times are the marks between 11 and 20? So 15, 13, and 20. So it's 3 times. Okay. And after that, you plot it. Wait. We also talked about a box plot, which is basically used to depict distribution of more than one groups of numeric data. Right. So a box plot is basically has the following components. So the middle line in the middle is the median, where the box starts is the Q1, where the box ends is Q3. So this is quartile 1, quartile 3. The area between this, where the box is drawn, is called the interquartile range. Okay. The minimum is basically Q1 minus 1.5 into IQR, interquartile range. Maximum is Q3 plus 1.5 into IQR. These lines are called whiskers. Any more dots are called outliers. Okay. So for example, here we have the median, the black line. Q1 is here, Q3 is here, Q2. These are called whiskers or the maximum and minimum of our data. And in this case, we have an outlier which falls outside the maximum. Okay. Maximum is defined as Q3 plus 1.5 into IQR. Minimum is defined as Q1 minus 1.5 into IQR. Yeah. We also talked about heat map, which can help us to visually understand the different values that might be there in a matrix, or visually access a numeric matrix or find patterns in data. We also talked about volcano plot, which is a specific type of scatter plot used to use mostly in genomics and proteomics. So here what we have is basically on the x-axis we have log 2 fold change, and on the y-axis we have negative log of the p-value. So we have cutoffs. So fold change, we have a cutoff of, because this is log 2 fold change, we have a cutoff of -1 and 1. So you want to know which genes have activity greater than uh, twice the activity in normal, so two-fold change, or less than half. So half fold change, right? And the other line here is basically for p-value 0.05. So anything that falls on this side of the plot, volcano plot, is basically down-regulated. Anything that falls on this side is up-regulated. And things in the middle are either not down-regulated or up-regulated enough, or they are non-significant statistically. Right. Then we talked about ggplot. So ggplot is basically grammar of graphics. It makes graphics by connecting multiple grammatical elements. There are three basic major grammatical elements, which is the data, which tells us what to plot, geometry, which tells ggplot what kind of plot to make, and aesthetics, which tells it what goes where. So what is the x-axis, what is the y-axis, and how to color the data, and so on. We also have other grammatical elements such as statistics, coordinates, statistics, which tells us how to transform the data, coordinates, which basically help us choose different coordinate systems to plot, facets, which can help us do multiple kinds of uh, subgraphs and arrangements, and themes, which is basically on all non-data ink. How does the plot look visually? Background, grid lines, etc. That's determined by the themes. Right. Okay, one question. Sir, what kind of questions could be asked in plots other than the function of arguments and maximum and minimum values? Okay, so we don't have a plot question. So these are the kinds of questions that you might get. Some of the more calculative questions might be like this. So instead of this, you might be given a plot. So let's say you're given a plot like this, where you have a box plot, where you're shown, and you're given some value. For example, you're given the Q1 and Q3, right? These values you are given. Then you are asked, this is an outlier. Which of the following data can be the outlier? You have a plot, you have Q1, Q3, and you are asked to calculate this. So this is basically the same question, but with a plot. Right. Other things can be this. So you can be asked like, so for example, you might be given plot of a code of a plot, and then asked what will it plot, or how will the plot look. For example, as we are asked here, we are given a code and we are asked what is P2. So basically, what is the plot? So it's a line plot with A and B on the horizontal and vertical axes. Questions like this might be things that you get, right? Or you get questions like this where you are asking, you have a data set of this type, or you have some data in this form. How do you visualize this, or what plot will you use? Right. So, for example, in this case, we have a data matrix of 20 rows and 40 columns. We want to create an image where colors represent numeric values. What type of plot do we want? We want a heat map, right? Then you might be asked questions like this, where you are asked to analyze some code. So you are given two plots. Now you are asked to find what is the difference between this. Maybe it might be changed that they can change it in some other way. So, for example, instead of X data, they write log of X data or something. And then they ask you what is the difference between these two plots, or how will they look, right? The general shape of the plot and things like that. Then they may ask you what does these functions do, what arguments do each functions these functions take, right? So things like that you might be asked in this case. Is that clear? So we also talked about networks. So networks are mathematically represented as graphs which have nodes and edges. So this circle is a node, and this line that connects different nodes is called an edge. Right. We can use networks to represent different entities, different things, such as our nodes can represent entities such as molecules or genes or persons, and our edges can be relations between the nodes. For example, proximity or correlated expression or regulation. Then we have different kinds of graphs, such as the undirected graphs, which don't have any direction, and directed graphs, where the flow of information is one side or the relationship is one side. Right. For example, if molecules are signaling and A activates something in B, something in C, but not the other way around. However, undirected graph, an example would be protein-protein interaction, where if A interacts with C, then C also interacts with A. Right. And we can use different kind of visual representations to put a lot of show a lot of different things on the graph, such as shape, size, and color. We can vary for the nodes and edges also. Right. We talked about adjacency matrix, which basically gives us which nodes are connected and which nodes are not connected. Right. We talked about undirected biological networks, such as gene co-expression network. Uh, We talked about how we can create a gene co-expression network using experimental data. So you basically calculate correlation, then you put a threshold on the correlation, and based on that, you assign nodes, right? We talked about directed biological networks, which is gene regulatory networks in E. coli, right? We also talked about different representations of networks. So we can arrange networks in different ways so that it conveys more information or something. For example, here we can see what are the different flowering genes in Brassica rapa. They are arranged in circles according to the different pathways that they exist in. So we can see the interactions within pathways and also between different pathways, right? And in this circos plot, uh, half of the data is basically cancer type and the other half is gene expression, and these connections basically show us what type of cancer has what type of gene expression, genes expressing more or less, right? So here are some tools that for network visualization that you might use later in later after you are done with the course and you are using maybe analyzing networks, right? Then session 5. In session 5, we talked about correlation and regression. So basically, we talked about covariance earlier. So we talked about covariance earlier, but we saw that covariance just tells you if there is some variance between x and y, if they vary together. But like if there is some relation, possible relation between them, but it does not provide us the strength of the relation that might exist between these variables, right? So that's why we need something which can give us the strength of uh, variance between two variables, and that is basically correlation. So we talked about different correlation coefficients that we can calculate from our data, such as Pearson's correlation coefficient, which is given by covariance of x and y divided by sigma of x into sigma of y. It varies from -1 to 1, where 0 represents that x and y are independent, right? The problem with Pearson correlation coefficient is that it does not capture non-linear relations. So we use something called Spearman rank correlation coefficient, where the basic formula is the same, But instead of using x and y as we are doing here, we are using the rank of x and rank of y. So rank is basically, so let's say for x, we have data 1, 1.2, and 0.8. We arrange it in ascending order. The lowest value gets the rank 1, the next value gets the rank 2, the next value gets the rank 3, and so on. We assign ranks. Similarly, for y, we can do the same. Then we can use these rank values to calculate the correlation. This again similar to Pearson's, it varies from -1 to 1 and it is 0 when x and y are independent. Then we have Kendall rank correlation coefficient where we take pair of observations and we check if it is concordant or discordant. So we take two pair of observations and then we basically see if the, so for example, if xj is greater than xi and yj is greater than yi, or if xj is less than xi and yj is less than yi, then these are called concordant pairs. Otherwise, these are called discordant pairs. Then, to calculate the Kendall correlation coefficient, you could just count the number of concordant pairs minus the number of discordant pairs divided by the total number of pairs. Right. And the most important thing to remember is that correlation does not imply causation. If two variables are correlated, that does not mean that one of them is causing the other. They might just be happening because something else is triggering both of them. Right. We talked about linear regression, where we are basically fitting data to a linear form of a model, y is equal to mx plus c. We talked about how we can use residual sum of squares to solve this using the least square method. So residual sum of square is basically yi minus mean of predicted yi whole square um, summation. So basically, y hat is the value that is predicted by our model. So we get something for the values that our model predicts based on the parameters M and C. We get some residual sum of squares. Then we try to minimize that residual sum of squares by modifying the value of M and C till we get at a appropriate value. In linear algebra, it's represented as the equation y is equal to x into m, where y is basically contains all the y parts, right? The y half of the equation. Values. X basically contains the value that you want to predict or fit to. X basically contains all the slopes or coefficients of the different predictors and the intercept. So this one is the intercept. And so basically all the variables that you are using, and this one is for the intercept. M is basically the matrix containing the slope and the intercept. So this is how it's expressed in linear algebra terms. And M is given as x transpose x, the inverse of that into x transpose y. Right. If you are doing multiple linear regressions, mm, you again can use the same formula to calculate the residual sum of squares and use least square method to get the result. In linear algebra terms, the equation is basically the same. However, the B matrix that we have, the coefficient matrix that we have here is much bigger compared to simple linear regression. In multiple linear regression arises the problem of multicollinearity, where we have this term of x transpose x inverse in our equation for B, which is basically the coefficient and intercept matrix. So for this equation to be solvable, x transpose x needs to be invertible, right? So it needs to be a full rank matrix. Thus, the columns and rows of X need to be linearly independent. So we can detect multicollinearity by using variance inflation factor and also by checking pairwise Pearson correlation coefficient between predictors. Variance inflation factor basically carries out auxiliary regression for each independent variable. By removing one variable and making it as the predictor, it carries out regression. It carries it out for all the different independent variables and then calculates the R square in each case. And VIF is defined as 1 by 1 minus R square. So if the VIF is greater than 10, then you should leave out a predictor from your sample, from your data set. Right. So the best thing to do if you have multicollinearity is to avoid it. So you design experiments so that you don't expect multicollinearity. Uh, in cases where you need to just do regression and only make predictions within the range of the data, you can still tolerate it. You don't need to do anything. However, if you have variables which have high VIF, you should remove them. Right. Then we talked about some diagnostic checks for linear regression. So we talked about the coefficient of determination R square, which tells us how good is our model compared to the mean model. Right. So R square is given by 1 minus residual sum square by total sum square. It varies from 0 to 1, where 0 is bad and 1 is perfected to data. For multiple linear regression, we have something called adjusted R square because the pure fact that in multiple linear regression, we are adding in more number of predictors brings an additional increase in accuracy. So basically, this R square will either increase or be the same if you keep adding predictors. So you have to account for that. So this adjusted R square basically penalizes the R square if the model parameters increase. So the more complex model you make, the less will be the adjusted R square value of that. Right. We talked, so this is basically recap of statistical test and t-test. So t-test we are basically using to compare sample means of two distributions. The null hypothesis is that the means are the same. The alternate hypothesis is that the means are different. Test statistic is something called t statistic. So it is sample statistics minus population parameter by standard error of sample statistics is given by this formula. Uh, it follows the t distribution with degrees of freedom n1 plus n2 minus 2, where n1 and n2 are the number of data points in both our samples. We compare the test statistics that we get to the t distribution critical value at a level of significance so that we can check if we have to reject our null hypothesis or not. Right. Uh, yeah. So the next thing we test for is basically t-test and ANOVA. So for linear regression, we do a t-test for the coefficient to see that does the coefficient make a difference? Okay. Is this model a good estimate of a real linear relation between X and Y in the population? Okay. So that is the question that it answers. If you find that some coefficient is not significant in this t-test, then you should remove those from your regression. For multiple linear regression, we have the same t-test for multiple coefficients. Along with that, we have a f-test, which is basically an ANOVA, which has the null hypothesis that all of our coefficients are, sorry, not ANOVA, f-test. So all of our coefficients are 0. And the alternate hypothesis is that at least one of them is not 0. So basically use this S statistic formula to check if uh, a model with several predictors is better than a model without any predictors. Right. Then we can also calculate the confidence interval for our regression coefficient, which is basically at some level of confidence alpha. It gives you around the sample mean, where is the population mean likely to lie. So this is given by B plus minus T. So this is T value of at the given level of significance into the sample variance. Right. So yes, how to decode eigenvalues and eigenvectors using data calculator. Most likely you won't be asked to calculate eigenvalues and eigenvectors. Okay. So don't worry about that. If you have any doubts, please ask in the discussion forum regarding this eigenvalues and eigenvectors. Most likely they won't ask you that in the exam, but if they do, they'll answer how to solve it using the calculator there. Okay. So in week 6, we talked about regression, clustering, and classification. So we talked about the different types of statistical learning. Unsupervised learning, where data is not labeled, and you are learning from the structure of the or the distribution of the data itself, such as clustering. Supervised learning, where data points have labels and you are learning by connecting the data to the label, such as regression or classification. Semi-supervised learning is basically where some data points have labels and that facilitates some sort of supervised learning. So, for example, semi-supervised clustering. We talked about nonlinear regression. So, linear regression is not able to capture nonlinear relation between predictors and response variables. So we can do nonlinear regression. The three approaches that we talked about: polynomial regression, linear regression post-linearization, and nonlinear least square method. Okay, so polynomial regression is basically, so let's say we have y is equal to x into b. So where the predictors are basically powers of x. So we are basically fitting this polynomial equation. Y is equal to a plus b1x plus b2x square plus dot 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 bk xk. Bk x raised to the power k. Right. So basically how we solve this is we basically convert it into a multiple linear regression problem. So by substituting x square as, so x is becomes z1, x square becomes z2, and so on, xk becomes zk. So basically we do this, and under some conditions we can do this and get away with it, where we get the solution of the for written here, x transpose x inverse into x transpose y. Then again, after polynomial regression, because we are doing some multiple linear regression, we can do a t-test for the individual coefficients. We can do a ANOVA to see if it's significant. And we can do an ANOVA to compare different models also. So let's say you have two models, y is equal to alpha plus beta 1 x, and M2 is y is equal to alpha plus beta 1 x plus beta 2 x square. Now, to compare these two models, our null hypothesis will be that B2 equal to 0, because then these two models will be the same. And our alternate hypothesis will be that B2 is not equal to 0. And then we basically use a F distribution and calculate, do the ANOVA and check if it's significant or not. So you need to know the concepts of these things, and you need to know how the uh, different functions, regression and t-test and all work in R, but you don't need to calculate anything by hand, so don't be worried about all that. Okay. So the other approaches for linear regression are linearization of a nonlinear system. So for example, if you have a system like this, we can tweak it to make it represent a linear equation of some other form, where our y and x values will be different, and then we can get at the original x and y using these y and x values, such as the original constant using these fitted values of b and a. Right. So basically, in this case, we are inverting the equation and we get the equation of this form, where our y is now 1 by y and our x is now 1 by x. So when we fit the equation, we get b and a is basically q by p and 1 by p. So using these two values, we can then get the value of p and q. Great. Nonlinear least square method is basically the same as how we did least square method for linear regression. So if you have a nonlinear equation, you basically have the actual observation minus what is the predicted value of the model based on the equation, and you sum this square of this error, which is the residual sum of squares basically, and you're trying to minimize these residual sum of squares for your model by changing your different A, B, and C parameter values. Right. So while choosing a nonlinear model, we need to be careful that we find a balance between model bias and model variance. So the model should not be very complex and not very simple also. It should be complex enough so that it can capture any nonlinear relations in our data, but it should not be complex, so complex that it overfits the data. So it can't make good predictions. Right. We also talked about clustering, which is basically the task of grouping a set of objects in such a way that objects in the same group are more like each other than to those in other groups. Right. We talked about types of clustering. So agglomerative and divisive clustering. So agglomerative is basically you combine things together to basically, so all the things you initially consider as a single, each of the elements are considered as single clusters, then you combine clusters to build bigger clusters. However, in divisive clustering, you basically have one cluster in the beginning consisting of all the data, and you divide it into different clusters based on some distance measure. Flat and hierarchical clustering, basically flat clustering is when you have just cluster data and you don't have the relation between each cluster or distance between each cluster. In hierarchical clustering, you basically show the relationship between each cluster, right? So for clustering, we need different distance measures to generate distances between different points so that we can cluster them. So the most common thing used as a distance measure for clustering is Euclidean distance, which is given as d is equal to xi minus yi whole square root over. So let's say we have points like x1, x2, y1, y2. So basically for element wise, we'll subtract it, square it, sum it, and take the root over of it. That is the Euclidean distance. In matrix formula, this is given as this. Manhattan distance is basically without the Euclidean distance without the squaring and the square root. So you just take the absolute difference between each corresponding element and sum it up. Minkowski distance is a generalized distance measure, which basically can be used to can be set. So basically, Minkowski distance is given as d is equal to summation of bar xi minus yi raised to power p whole to power 1 by p, where p is greater an integer greater than equal to 1. So if p is 1, we get Manhattan distance. If p is 2, we get Euclidean distance. Right. So this is a generalized distance measure that can be used to generate distance of different kinds. Then we have something called Mahalanobis distance, which is given as x minus y transpose into S inverse into x minus y, whereas this is the covariance matrix between x and y. Right. It is used when there might be correlation or relation between both the axes and they might not be independent of each other. When variance is 1 and x and y are not correlated, then this matrix basically turns out to be a identity matrix and the equation turns out to be a Euclidean distance. Or Euclidean distance. Right. Then we have other methods of distance measurement, such as chord distance, which is basically this distance, this point to this. This is a unit circle. We have something called correlation distance, which is basically covariance of x and y divided by standard deviation of x into standard deviation of y. So correlation, so this is basically the correlation. The correlation distance is 1 minus correlation of x and y divided by 2, right? So correlation, as we know, can vary from -1 to 1, where it is 0, x and y are independent. So correlation distance can vary from 1 to 0. If it is 1, then x and y are negatively correlated. If it is 0, then x and y are positively correlated. If it's 0.5, then x and y are independent. So if x and y are independent, it is 0.5, sorry. Then we have something called Hamming distance, which is basically, let's say you are comparing two strings or two DNA sequences. At each index, you compare if the value is equal or not. If it is not, then you keep 1. If it is equal, then you keep 0. And then you sum it up. So you get the Hamming distance. We also talked about classification. So classification is basically the process of identifying and grouping data into predetermined categories. So we first need to define some class labels or categories. Then we need to assign training data to specific classes and generate a model to place objects in different classes. Then we need to use this model to classify test data. Okay. Does anyone have any doubts till week 6, till what we have talked till now? Someone is typing. Sample question based on the distance measures. Okay. So, uh, let's say you're given 2 points. You're given the 3, 2, and you're asked what is the Euclidean distance between them. So, what do? Euclidean distance is given as 5. Right. Is it no? Xi minus y whole square. So basically 1 minus 3, 1 minus 3 whole square plus 1 minus 2 whole square root over. It's 2 square plus 1 square. 4 plus 1 root 5. Right. Then let's say you're given the same question and you are asked what is the distance between, what is the, what do you say? What is the Manhattan distance between them? Right. It's basically psi minus I is basically 1 minus 3 mod plus 1 minus 2 mod 2 plus 1 basically 3. You might be given questions such as, uh, let's say you're given 3 points. I draw. Let's say you're given another point here, 3 comma 1. Okay. And you're asked which of these points, where these are labeled A, B, C. Okay. You'll be asked which two of them are the closest to each other. So basically what you have to do, you have to take the, and you'll be given like what distance measure you need to use. So as we calculated here, sorry, you need to calculate the distance between A and C, distance between B and C, and distance between A and B. And then see which one is the smallest and basically choose that option or write it down. Right. Apart from that, for Hamming distance, the questions will be very similar to this. So mostly you'll be given some DNS equals and you'll be asked what is the Hamming distance between them. So you can basically see if the letters match, then there's a 0. If they don't match, there's a 1. Here 1, and basically you add them up, so you get 3 here. Right. Other things might be, you might be asked formulas for different distances. Right. Like it's asked here. You might be asked what is the formula of Mahalanobis distance, or what does the S in Mahalanobis distance stand for, right? Or why are we taking why are we taking S here? Because in Mahalanobis distance, the X and Y axis are correlated. So we want some measure of uh, covariance kind of to detangle that, right? Oh, okay. Yeah. So we're talking about classification. We talked about logistic regression. We talked about the sigmoid function. Then we talked about uh, odds ratio. So it's basically probability of x divided by 1 minus probability of x. This is the odds ratio. And if you take a log of it, it's called log odds or logic, right? Uh, we talked about maximum likelihood. So basically, sorry. So we are given some data. We are trying to fit some model to it. So we are trying to fit a model of this type. So how will we fit that? So we'll basically see for each of our data sets, what is the likelihood of our data set occurring given these values of A and B. And then we keep on tweaking values of A and B so that the likelihood value we get will be maximized. So you want to maximize the probability of seeing the observed data that we have actually seen given the parameters of the model. Right. If we have multiple predictors in classes, we can modify the equation to something like this, the sigmoid equation and the whole fitting equation also. Right. And if we have multi-class classification, what we can do is we can create binary models for each class. So model, let's say you have three classes, then you create three models. Model one will just check if it is category one or not. Model 2 will just check if it is category 2 or not. Model 3 will check if it is category 3 or not. And when we are taking the predictions, we basically pool the answers from all three models. Right. We talked about confusion matrix, which is a performance evaluation tool for classification models. So we have a matrix like this, where the predicted values are on the left side, on the rows, and the actual values are on the columns. Right. We get numbers here. So this is called true positive. It is a positive value predicted as a positive value. There is a false positive because it's a negative value predicted as a positive value. This is a true negative because it's a negative predicted as negative. It's a false negative because the negative positive predicted as negative. Right. So based on all this, we have different measures that we can calculate to see how our model is doing. So sensitivity or the true positive rate tells us how many positive cases are identified from the whole data. So it's basically true positive divided by the total number of positives. True positive plus false negative. Right. Specificity, it tells us how many of our negative cases are truly negative. So for example, it's true negative divided by total number of negative. True negative plus false positive. Right. So let's say we have a model that is predicting whether a person is sick or healthy based on something, right? So positive here means sick and negative here means healthy, right? So true positive will be when a sick person is predicted as sick. True negative will be when a healthy person is predicted as healthy. So in this case, our sensitivity is basically how many of the sick populations in the whole sick persons in the whole population did we identify? So basically, how many of the total positives did you get as true positives? Right. And then the specificity in this case will be how many of the people who are predicted as healthy are actually healthy. So how many of the negative predictions are truly negative? Right. Uh, so sample question based on this would be, let's say you are given a model. You're given some confusion matrix. You're given some value, let's say 20, 25, 10. Right. This is 50. Huh. So you're given these values and you're asked what is the sensitivity of the model. So sensitivity will be equal to true positive. So let's say this is 1 positive, basically 1 0 1 0 as the layout as here. So these are the actual values, these are the model values. right? So true positive sensitivity is given by true positive, given as true positive by true positive plus false negative. So we have true positives here. We have false negatives here. What will we do? 20 divided by 20 plus 10, which is 2 by 3. And again, for specificity, if we are asked to calculate specificity, sorry, it's given as true negative by true negative plus false positive. Basically, this divided by sum of these. 15 divided by 15 plus 5. 15 by 20. 3 by 4. Right. These are the kinds of questions you might get on this. Most likely you won't get these kinds of questions, but if you get, they might be like this. Then we yeah, sorry. Yeah, someone is typing. Uh, okay, sorry. Yeah. So this is week 6. Then week 7, we talked about clustering and classification. So basically, we talked about k-means clustering algorithm, how it works. It's an unsupervised statistical learning method where we are iteratively assigning data points to clusters based on distance from cluster center. So first we specify some number of clusters. We randomly assign some centroids for the clusters. We calculate the distance of the centroids from each data point, and then whichever each data point gets assigned to its closest cluster centroid, right? Then, after we have assigned data to different clusters, we again calculate the centroid of the data. So the centroid will now shift to somewhere else. And then, based on the new centroid, we'll again assign data points. And this whole thing will keep repeating till our centroid is fixed or till the maximum number of repetitions we want to do is achieved. Right. So this is k-means clustering. To evaluate the result of k-means clustering, we can use something called within cluster sum of squares. Okay, so it basically measures the variability of data points within each cluster. So if we are saying some kind of clustering is better than another, then one possible reason might be that because the cluster is basically tight. So all the points in the cluster are close to each other. So basically this measures the same thing. What is the variability of data points within each cluster? If there's a high variability, then the model is bad. If there's a low variability, that means the clusters are tighter and the model is better. So in k-means clustering, to choose the optimum number of uh, clusters, K, what we do is for the same data set, we run k-means clustering for multiple values of K, 1, 2, 3, 4, and so on. And then we plot the value of WCSS or within cluster sum of squares. And this plot is called a elbow plot. So initially, you see as you keep increasing the K, the within cluster sum of squares will decrease quite rapidly. However, after a point, after the point of inflection or after some point, it stops decreasing that rapidly. So after that, so this is where you can basically draw a line and decide on the optimum number of clusters based on the elbow plot. Hierarchical clustering is basically where you is another type of clustering. It's a agglomerative type of clustering. So we are basically assuming everything as independent clusters and then building up relations between those. Uh, so making them into bigger clusters. So basically, initially we have all our data. We see which two data points are closer. Then we assign them to one cluster. And the distance, half of the distance between them is depicted here. So the length of the line is half of the distance between them. Then what we do, then we see which of these things. So if the cluster AB is closer to C or D, or if C and D are close to each other. So we find that, let's say in this case, AB is closer to the cluster AB is closer to C. So in that case, the next step would be to join C with A and B, and this will be the height of this will be half of distance between AB and C. And similarly, we carry it forward for all the data points and all the clusters till we finally arrive at one single cluster. Okay, the hierarchical relations between different clusters is again shown using a dendrogram. The main benefit of this method is that we don't need to a priori specify the number of clusters, right? As I talked here and before also, we need to, in some cases, find out the distance between clusters or the distance between a cluster and a point. So the distance between two clusters is called linkage. There are four types of linkage that we can calculate. One is called centroid linkage. There you calculate the centroid of both the clusters that you want the distance from, and you take the distance between the centroids as the distance between the two clusters. Okay. Uh, then for the rest of the other three kinds of linkages, you need to calculate the pairwise distances between all the elements of the two clusters. Single linkage is basically the minimum of those pairwise distances, right? Complete linkage is the maximum of those pairwise distances, and average linkage is the average value of those pairwise distances. Okay, so the outcome of your clustering will depend on the distance measured for data points, the Euclidean distance, Mahalan-Nouveau distance, or whatever you take, Manhattan distance, and the linkage measure that you take. So you should be careful while picking these values out for your analysis. We also talked about decision trees. So decision tree is basically a classification model which asks a question at each step, and then based on the question divides the data into two parts. In this case, so it's a binary decision tree. It divides into two parts. Then it can ask more questions of about the subset of data, or it can label the subset of data into a given class or something. Right. So how does this occur? How does the decision tree basically work? So initially, so we need a way to basically check where to stop, and we also need a way to check what question to ask. So to check where to stop, we calculate something called purity. So if this subset of data is pure enough, if it contains maximum, if maximum of the examples of this subset are from class 2, and there are only a few subsets from class 1, then we can label this as class 2, right? So that's how purity comes in. And the other thing is, uh, how do we ask these questions? We use something called, we basically compare different questions by comparing splits, by using something called information gain. So purity, as I mentioned before, which helps us stop wherever we want, is determine where we should stop, is basically so there are two different measures of purity. One is called Gini index, and it's called entropy. Gini index is given as summation of fmj into 1 minus fmj. Fmj is fraction of observations of class J in the mth region. Right. So these are broadly our regions, and what is the number of uh, examples of a particular class in that region. Right. Entropy is again similar in a way, but slightly different. It again follows this thing. Uses this fraction of observations of class J in mth region and uses the log to calculate the entropy. So both these graphs, entropy and Gini index, look like this when you plot it with the probability of uh, points in one class. So if the this is a binary classification problem where 0 represents one class and 1 represents the other class. So if the samples are very pure, or if they contain mostly examples of one class or the other class, then the entropy or the Gini index value will be very low. However, if the data subset of data contains homogeneous data, the value of entropy or Gini index will be very high. Okay. Comparing splits is basically when we are, so let's say here we are asking a question, G1 is less than equal to 4. How do we know to ask this question and not something else? So for that, what we can use is something called information gain. So let's say we have this structure where at each point we calculate the entropy or the Gini index or whatever entropy in this case we are calculating. Then we have another question, and again for that question we calculate the entropy. Then using this formula for information gain, we want to maximize the information gain. So basically, HP is entropy of parent, HC1 is entropy of child 1, HC2 is entropy of child 2, FC1 is proportion of points in C1, FC2 is proportion of points in C2, मतलब class 1 and class 2. Using this formula, you want to maximize information gain. So whichever question gives us the maximal information gain, we'll use that question. Okay. For using a decision tree to make predictions, if you have some data points, you basically keep answering the questions. So we have the data point G1 equal to 3 and G2 equal to 2.5. So here the question is G2 is less than equal to 3. The answer is yes. So we go here. Then G1 is less than equal to 4. The answer is yes. So we go here and we arrive at a leaf node or a node with a prediction. Yeah, so basically in a decision tree, these nodes, the ending nodes are called leaf nodes. The starting node is the root node, and anything in between are called internal nodes. Okay. So decision tree has very low bias, so it can compartmentalize and fit to data very well. It has a very high variance, so it has less predictive capability. So one way to build a balanced decision tree is to boost it or do something called bagging or bootstrap aggregation. So random forest classifier is one example where we do bootstrap aggregation of decision trees. So as mentioned, random forest classifier has two steps, bootstrapping and aggregation. So bootstrapping is basically we have all of our data, n samples into p predictors. We divide it into different subsets with S number of samples and M number of predictors. In each subset, we train a decision tree. So basically, this is called bootstrapping, the whole process, where we are dividing our data into different subsets and then training on those subsets. Then the next step, aggregation, is used when we are basically predicting. So basically, when we are predicting, we take predictions from each of the decision trees and then take the majority vote. Right. One thing to remember is that it's bootstrapping. This bootstrapping is done with replacement. So whenever we are picking a sample, we are putting it back in and then picking up again. Right. Then we talked about maximal. Okay. So, so about linkage, let's say. So boosting and bagging, I don't think you will get questions on that. So don't worry about that. You will get some code questions mostly. So it will be example how to run a random forest or how to run some classification algorithm. That kind of questions you'll get. Uh, yeah, other kind of questions I don't think. But for linkage and all, you can get questions for calculation. So for example, let's say you have uh, a plot like this, where you have one, this is two, one, this is four, one, this is five, two, let's say. Okay. So we know that this is C1, cluster 1, and we know that this is cluster 2, C2. Okay. So you are asked what is the average linkage between these two. The average linkage, how will you calculate? So to calculate average linkage, single linkage or complete linkage, you need to calculate the pairwise distances first. So for all these points, you need to calculate the pairwise distance. So let's label these points A, B, C, D. And let's say we are using the Euclidean distance. So we'll calculate the distance between A and B is basically 2 minus 1. This is 1. Then distance between, sorry, my bad. So we don't want distance between A and B because they are in the same cluster. What we want is distance between A and B, distance between A and C, distance between B and D, and distance between B and C. So these 4 things we need. So AD will be 5 minus 2 whole square plus 2 minus 1 whole square. Right. So this is 3 square, 9 plus 1 square 1. This is root over of 10. Then AC will be 4 minus 2 whole square plus 1 minus 1 whole square. This is 2 square 4. This 2. BD will be 5 minus 1 whole square plus 2 minus 1 whole square. So it's basically 4 square 16 plus 1 square 1 root over of 17. And BC will be 4 minus 1 whole square plus 1 minus 1 whole square. So this is 3 square, 9, and this is 0, this is 3. So these are the distances that we got. Now to calculate the average linkage, all we need to do is we need to take the average of these distances. So root 10 plus 2 plus root 17 plus 3 divided by 4. So you can use the calculator now to figure this out. Right. Now if you want the single linkage, so root 17 will be somewhere around 4 point something. Root 10 will be somewhere around 2 point something. So the single linkage here will be 2 because 2 is the least distance that we get. And the complete linkage here will be uh, basically root over of 17 because that is the maximum. That should be the maximum distance. Right. And as for this, so this I think we did in the class. So let's say it's basically just a proportion. So let's say you have class 1 and class 2, and you have, let's say, here you have M. So M is basically your region. Region. So in region, let's say in region 1, you have this much proportion of 1 and this much proportion of 2. In region 2, you have 0.5 proportion of each. In region 3, you have 0 of this and 1 of this. And in region 4, you have 0.25 and 0.75. And you are asked what is the Gini index of region 4. Right. So Gini index will be asked for a region. So Gini index of region 4 will be, so this is for class 1, what is the fraction? 0.25 into 1 minus 0.25 plus for class 2, what is the fraction? So how many ever classes we have, we do it for that. So it's 0.75 into 1 minus 0.75 is basically 2 into 0.25 into 0.75. 0.375 or something should come. Hmm. Okay. Yeah. Maximal margin classifier is basically uh, a classifier which draws a margin, which draws a boundary between two classes of data. So and it has something called a margin. So margin is basically the distance between the closest data point to the decision boundary. Okay. A maximal margin classifier basically finds a decision boundary that maximizes the margin. Okay. In most cases, the optimum position of the decision boundary will be halfway between the closest positive and negative data points, right? And these closest data points that are basically uh, on the margin are called the support vectors, right? Uh, so these are the data points that affect the boundary. The other data points do not affect the boundary. The limitations of maximum margin classifier are that small changes to the training data, especially the support vector, can lead to large changes in the classifier, and it tends to misclassify a test sample near the boundary. Okay. So we come across support vector classifier, which basically use the principle of maximum margin classifier, but with a soft margin. So what is a soft margin? So a soft margin basically allows a few training data to be within the margin and allows a few of the training data to be on the opposite side of the margin also. So there's a tuning parameter called C, which can be used to restrict the extent of this, right? And it tends to avoid overfitting to the training data and can handle nonlinear examples to certain extent. So this is called support vector classifier. But to do proper nonlinear classification or to fit nonlinear decision boundaries, we use something called a support vector machine, which is an extension of support vector classifier that basically transforms your initial predictor space into some higher dimension and then uh, tries to find boundaries in that higher dimension that might be able to help you segregate the data. So for example, let's say we have some data like this, then what we can do is we can change this data into 3D by transforming one of the axes so that we get data like this. And then we can actually get a plane of division right in between these two different classes. And when we then transform back to our original dimension, we get that the plane is actually a curved line like this in our lower dimension. Okay, so that's all about support vector machines in week 7. Then in week 8, which was last week, we talked about higher dimensional data in R. We talked about experiments, how to so these high dimensional data might be difficult to visualize and extract meaningful quantitative information from. So we do dimensionality reduction, where we basically create new dimensions by combining the original one. Two common methods used in biology are PCA and TSNE. In PCA, basically what we are trying to do is we are trying to capture the axis of highest variation in the data. So we basically change the coordinate system such that the new coordinates capture the most variance in decreasing order. So the new x coordinate will have the most variance. The new y coordinate will have slightly lesser variance than that. The z coordinate will have lesser variance than that, and so on. Right. And the only thing is, these axes that we create in PC are all orthogonal to each other. right? So we have some data of this form. We want to basically project it to a vector u such that where u is a unit vector, we want to project it such that the variance of the projected data is the maximum, right? So for that, we use the covariance matrix and we find the eigenvalues and eigenvectors of the covariance matrix, right? And that's how we define PCA. So basically, PCA is we are projecting X on another unit vector U such that we maximize the variance. So the objective function is here maximizing the variance of XU by varying the value of U. Okay. And if you do some mathematics, you can show that XU is given as U transpose S into U, where S is the covariance matrix of X. Okay. And the solution to this objective optimization problem will be SU is equal to lambda U, where basically U is our eigenvector of the covariance matrix that we have, and lambda is the corresponding eigenvalue. So the eigenvectors in PCA become the new axis after PCA. So these are called the principal components, and the eigenvalues basically uh, are the variance of the data on that particular eigenvector axis. Okay. So again, just to reiterate, I am not sure if you will get how to if you get questions on how to calculate eigenvectors and eigenvalues, but most likely you should not get questions on that. If you still have doubts and you want to know how to do it on the calculator and how to solve for it, please ask in the discussion forum. Okay. But most likely you won't get questions where you are asked to find the eigenvalues and eigenvectors of different uh, data. Okay. So basically, yeah. So we arrange all these eigenvalues or the variance in the descending order, and we take only a few of these axes. So we'll have d such axes where d was our original dimensions also. However, we just take a few axes because we want to reduce our dimensions, and we take fewer axes which capture most of the variation in the data. Okay. So to select the principal components, we plot something called a scree plot, which is basically like another elbow plot. So here we have proportion of variance explained on the y-axis and the PCA basically the vectors, the principal components. So you see that as we go further, the proportion of variance explained decreases, and after a point, it will start plateauing where you should stop taking any more values. And based on this scree plot, you can decide how many number of different variables you want. Okay. What kind of questions can come on PCA? So on PCA, you will get questions like this, where you might be asked to calculate what is the fraction of variance explained by some principal component. Okay. Or you might get questions like this, where you will be asked about different functions that might be used to carry out a PCA. You might be asked how to carry which function in R is used to carry out a PCA, which is PRComp, right? You can be asked other things like true or false statements about PCA and all, right? So what kind of technique it is, what does it do, what is the principle behind it, and all that. You need to be clear about all that. You don't need to calculate eigenvectors and eigenvalues for anything. Okay. So basically, if we express it in linear algebra term, we have three matrices. We have the centered data. So the data for PCA should always be centered and scaled. Is the centered data, which has dimensions n cross d, where n is the number of samples and d is the number of variables, which is multiplied by v, which has dimensions d cross m, where d is basically the number of variables and m is the number of selected principal components. So this V matrix is called the loading matrix, which contains how many ever selected principal components we want. Okay. And T is basically the projected data, the data in the reduced dimensions, which now has the dimensions n cross m, where n is the number of samples and m is the number of dimensions we want it to be. This is again called the scores matrix. Right. So this is basically a recap of PCA. Then we talked about SNE, stochastic neighbor embedding, where basically we are embedding data from higher dimension to lower dimension by preserving neighborhood identity. So we calculate a distance or dissimilarity between 2 points. Then we calculate some probabilistic similarity measure between them. Okay, Pij. Uh, with this, basically, we are using a normal distribution to calculate this value. And the sigma here in this equation is controlled by a tuning parameter called perplexity. Okay. Similarly, on the lower dimensions, we arrange all our points randomly and we calculate the Euclidean distance between all pairs of points. Then we use this Euclidean distance using a similar equation from the normal distribution to calculate Qij. Okay. Then we try to map Pij onto Qij. So basically, the distance in the higher dimensions, we are trying to map it into the lower dimensions also. Okay. So we compare for all of it and we repeatedly rearrange the data so that we maximize the this log ratio of this Pij and Qij. Right. So yeah, this will be maximum when Pij and Qij are mapping to each other, one is to one, perfectly mapping onto each other. So yeah, so we want to get as much higher value as possible. That is SNE. TSNE is basically stochastic neighbor embedding with a T distribution. So here in the second part where we are calculating the Qij in the lower dimension, what we are using is a T distribution. So we are using this formula to calculate the Qij, not the formula from the normal distribution. So what does this do basically? It basically moves close points closer and far points farther apart. So let's say we have some point at a distance of 2 units on the higher dimension. So if we use so we are basically using the normal distribution to map it to some probability value. Then based on the probability value, we use a t distribution. So as you might remember, a t distribution has a lower height and a fatter tail. So a t distribution, this value maps onto 1.5, which is closer. However, let's say we had a value which is, let's say, 3.5 in our original higher dimensional space. So 3.5 gets mapped onto this value by the normal distribution, which then gets mapped onto this value by the t distribution, which is 5. So basically, if the points are farther apart, we are pushing them apart. If they're closer together, we are pulling them together. Okay. So this sigma value is controlled, the sigma thing here in this equation, and in that equation, and is controlled by something called a tuning parameter called perplexity. So it basically balances between the local and global aspects of the data, and it's recommended that it should be smaller than the number of data points that you have, and the suggested range is between 5 to 50. Be careful where you are using PCA or TSNE to basically visualize data, because these are data visualization techniques. These are not clustering techniques. So any cluster you get or any cluster size or distance between clusters that you get might not be representative of the actual thing in higher dimensions. Okay. Then we also talked about diffusion maps. So diffusion map is a nonlinear dimensionality reduction technique which integrates local information to generate global description of the data. It's more robust to noise. So it basically follows a diffusion over data points kind of model. So let's say you have these 4 data points in higher dimension. You put a marble on some of it and you let it freely flow. So where does it go? That is basically diffusion. We want to quantify this thing. So to quantify this, we quantify something called the transition probability, which basically gives us the probability of going from, let's say, data point x1 to data point x3 or x1 to x2 from A to B in general. So this transition probability is given as this. Then we generate a matrix for all of our data points. It's a square matrix. So data point 1 to data point 1, what is the transition probability? Data point 2 to data point 1, what is the transition probability? 1 to 2, 2 to 2, and so on. We calculate for all our data points. The interesting properties of this transition matrix. One is that one eigenvalue of this transition matrix is always 1, and the rest of the eigenvalues are less than or equal to 1. Okay. Another important thing or interesting thing is that if you multiply this matrix by itself, so if you take powers of the matrix, you basically get what is the sum of probabilities of all paths of length t from the data point xi to xj. So for example, p1 to 1 is basically the probability of transition probability, sum of all probability of ending up at 1. You're starting up at 1 and ending up at 1 in t steps. So for example, if t is 3, then we can go from here to here one step, one step, one step. This will be one path. Another path will be here, here, and then back again. Another path might be here, here, and then back to here. So the value that you get here will be sum of the probabilities of all such paths of length t. Okay. So diffusion distance in higher dimension is given by this. So the t value is something that you choose. Mathematically, it can be shown that the matrix PT that you have, the rows of the matrix are basically equal to the diffusion distance in higher dimensions. Okay. So if you basically plot data in dimensions of this, so this PT matrix, which is n cross n, where n is the number of samples, if you plot it in this dimension, it will basically preserve the diffusion distance between the different data points. So in this case, we get a dimensionality reduction to n. And after that, what we do, we can go to even lower dimension. So as I mentioned before, this probability transition matrix has interesting properties. So the first eigenvalue is 1, and the eigenvector that we get is basically a constant eigenvector that we are not interested in. So this one we can eradicate and not look at. So we'll discard it, lambda 0 and psi 0. So we can reduce one dimension. So now we have n minus 1 dimensions. Then what we can do to reduce dimensions even further is that, so we arrange all the eigenvalues in descending order. Okay. And then take only few of them which are considerable enough, and we discard the rest of them. So for example, in this case, if we get three eigenvalues that are considerable enough for us, then what we get here is we reduce it to 3 dimensions basically. And then we talked about some example of diffusion. So we talked about in most of the towards the end of it, the things that we talked about. It's basically more about the model and embedding and all, and how to do it. So the questions that you will get will be on the understanding of the models. So how do the model works? How do you calculate variance between the model, or how do you like see if it's a good model or not? Then some true or false things about those models. Then how can we run those models in R? So these kinds of questions are the questions that you will get from this last week exercises. Okay. Does anyone have any doubts or questions? Okay. If no one has any more questions, we'll stop here. All the best for your exams. If you have any more doubts or any other questions, uh, do post it on the discussion forum. Even now, I think they'll answer all the questions before the exams. If you have any more questions, you can ask them right now, or we'll not meet anymore. Anyways, all the best for your exam. And yeah, thanks a lot for attending these classes. We'll see you later. Yeah, bye.